in section 11.5, we will learn about different applications of the lines and planes in space. Okay. First of all, we're going to define a vector equation for a line. So if I have a point a point P, x of 0, y of 0, z of 0, that is parallel to some vector v, then we can write a vector equation for the position of that vector. We call it the position. So we call it r sub t in terms of what we call a parameter. Okay, the parameter t is gonna give basically it gives us a better description of a vector's position, starting position, and ending position as we increased the value of the parameter t. So the vector, the position of the vector would be the initial position, we call it r sub 0, plus the vector v by some increasing parameter t. So also we can parameterize a vector. Okay, we can write parametric equations for a vector that will give us all the different points that go through that belong to this vector v as we increase the value or decrease the value of t, which is called a parameter. So the parametric equation, as discussed in precalculus, it is going to be x equals to the initial position of my x value, which is x of 0. Basically, that would be the point where the vector begins, the x coordinate of where the vector begins, plus the x component of your vector v times some parameter t. Okay, so and that will tell us that as we increase the parameter t, then if let's say we start with t equals to 0, that is going to give us the starting position of the vector, which will be x of 0. Okay. Likewise with the the parametric equation for the y value, it would be y equals to the initial value of y of the vector plus the y component of the vector times some parameter t, and that will give us, for example, if t is equal to 0, then we're going to get the initial position of the y value, which is y of 0. And then as we increase the value of t, that's going to give us all the points that will belong to this vector v. And third, to find the value of z, it would be z equals to the initial position, which is z of 0, plus then the z component times some parameter t. That will give us all the values of z that will belong to this vector v. Okay. So let's start with this. We have that a line passes through the points p equals 597 and q equals -3, 3, -5. Find the standard parametric equations for the line written using the base point p equals 597 and the components of the vector pq. So we want a parametric equations for the line that passes through that vector pq. So first of all, we need to find that vector pq. So to find it, we're going to subtract the x components, the y components, and the z components, and we're going to write it in terms of I, j, and k. Okay, so the first one would be, it's going in the direction of q, so it would be q minus p. Okay, so -3 minus 5, that would be the first one. And then the y components, it's 3 minus 9. Let's give it a second so it's for it to load. And the last component would be -5 minus 7. So that's going to give us the vector pq, which is going to be defined as -8i plus, well, I can just write it as minus 6j and then minus 12k. This is the vector in which the vector that is traveling from P to Q. Okay, the direction of that vector. So now, if we want to find a parametric equation for the line that passes through that vector, first of all, we need to start with this. To find the x value, we need the initial position of the vector, and this is telling us that it's going to start from point P. So that is going to be my initial point. So my initial x value would be 5, and then it's going to be increasing by this x value, which is -8. That's the x component of the vector PQ. So instead of putting plus, I'm going to put -8 times some parameter t. So then we're going to do the same thing for the y value. It's going to start from the y equals to 9. That is my starting point. And then it's going to be changing by this component. The y value, that's with my j component. So it will be changing by -6 times some parameter t. And the z value is going to have an initial value of 7, and it's going to be changing by -12 times some parameter t. Okay, given that, remember that t is any number from -infinity to +infinity. So if I say, for example, that, let's just give it an example. If I let the t be 0, okay, so this is just an example that I'm going to put here. If I let the t be equal to 0, what are we going to get? X equals to 5, y equals to 9, and z equals to 7, which is the 0.597, and we realize that that is the starting point of this vector v, well, vector PQ, right? And now let me tell you this. What if we let the t be equals to 1? So 5 minus 8 is going to be -3. For the y, 9 minus 6 is going to be 3. And for the z, 7 minus 12 is going to be -5. So you're going to get the point -3, comma 3, comma -5. What do you notice? That's the point Q. And if we substitute any other values of t on this line, it's gonna create all the, not only these two, but all the points that will be on this vector PQ. Okay, so these are my answers for the parametric equations for the line that passes through this vector PQ. Next, find the parametric equations for the line through 9, -8, 9 parallel to the x-axis. Okay. Now, I want you to think of a line that is parallel to the x-axis before I actually get the equation so you can visualize it. You don't need to draw a sketch, but this is going to help us understand something. What if I have a line that is parallel to the x-axis? We're talking about something like this, right? That is a line that is parallel to the x-axis. Yes? What can we say about that line that is parallel to the x-axis if we look at any points on this line? What do you notice about the value of y of that line that is parallel to the x-axis? This is my x-axis, right? We see that the values of y are all staying the same. What else can we say? The values of z right here, whatever the z is, are all staying the same, right? Because it has to be parallel. What is the only thing that is changing on that line? The x value. So the x value is the only thing that is changing as we move from one point to the next point to the next point. So any line that is parallel to the x-axis in the coordinate and the coordinate plane x, y, z in the triple coordinate, it's gonna have the following properties: that the y and the z will always remain constants. Okay, the y and the z will be constants. The only thing that will be changing is the x. Why am I saying this? Because to get the parametric equations, that's exactly what we're going to use. Okay, since the y and the z are going to remain constants, so the y, it's going to, again, this is the starting point. So the y is going to start at -8 and is not going to change, meaning that it's not going to contain a parameter, because the parameter is what makes the point to change from one point to the next to the next. But in this case, there is no parameter because the y must be constant. the next one, we also said that the z must be constant. So it's going to start from 9 and it's going to stay at 9. And last but not least, the only thing that is going to be changing is going to be the x. So the x is going to start from this 9 right here, and it's going to be changing by some parameter t. Okay? So as we increase the value of t, that's going to give us basically all of the changes for that value of x, and where the y and the z will stay constants regardless of the value of t that we assign, and that will basically generate all of the points on this line that is parallel to the x-axis, keeping the y at -8 and keeping the z at 9. Basically, it's going to be a line that is parallel right here to this axis. Okay? And we just have to specify that the t, it's going to be any number from -infinity to +infinity. That will assure us, that will generate for any given value of t, we're going to generate all of the points that will lie on this line that is parallel to the x-axis. Next, now find the parametric equations for the line through -2, 5, -5 perpendicular to the plane. 3, 10, 4, 3x plus 10y plus 4z equals to 11. For this, let's keep one thing in mind, and that is that any vector that has the same components as the components of a plane, the same components meaning this component for the x, this component for the y, my I, my j, my k, if we create a vector with these components of a plane, that vector will always be normal to the plane. Normal means perpendicular. So that's gonna, if I create this vector, so that would be 3i plus 10j plus 4k. If we were to sketch this plane and this vector will always be perpendicular to that plane. Okay, so we're gonna get into sketching planes and in the 3 dimensions later. This is just one of the properties. So now, what do we know? We want an equation that passes through this point, so we can use this as our initial point. So I'm going to use it as my x of 0, y of 0, and z of 0. And I want it to be perpendicular to this plane, so these are the components of a vector that will be perpendicular to that plane. So to create those parametric equations, we're going to start with the x equals to -2 plus, and then my x component of the vector that is perpendicular to the plane, which is 3i, 3 times some parameter t. We want to write it in terms of a parameter. So then y equals to my initial value for the y, which is going to be 5, plus 10, which is the y component of the line that is perpendicular to that plane, times some parameter t. And then z equals to the initial value for z, which is -5, plus 4, which is the z component of the line perpendicular to the plane, times some parameter t. And since these components are perpendicular to this plane, then these 3 lines that pass through this point, starting at this point, will be the lines that will be perpendicular to this plane. 3x plus 10y plus 4z equals to 11. Okay. So let's go ahead and say now the parameter t, it's going to be any number from -infinity all the way to +infinity. Next. Now we're going to find the parametrization for the line segment joining the points P0, 6, 0. Now on this one, we want to restrict the parameter since we want a line segment. We just want the line segment starting at P and ending at Q specifically. Okay? And then we're going to draw it. So, first of all, we need to find the vector that contains those 2 points, vector PQ, from P to Q. So we're going to subtract the components to get the I component, subtract the Y components to get the J component, and subtract the Z components to get my K component. So it would be from P to Q, then we're going to do Q minus P. So it would be 0 minus 0. That would be 0I. Then negative 6 minus 6, which is going to be minus 12J. And the last one is 6 minus 6, which is going to be plus 0K. So this is a vector that goes from P to Q. Okay. So now we're going to write parametric equations for that vector, taking the 0, 6, 6. Let's take it as my initial point. Okay. So I'm going to say that x is equal to my initial point of value of 0 plus, and then my x component is going to be 0 times some parameter t. Mainly, since it is both zeros, then it's going to be just x equals 0. So that's just a constant at 0. Okay. Then we're going to start with the y. The y is going to be, my initial value for the y is 6. So it would be 6. And then the y component of the vector would be minus 12 times some parameter t. Okay. So that one stays the same. So it would be 6 minus 12t. And last but not least, we got the z. Z equals to my starting value of z, which is 6, plus 0, which is the component for the z, times some parameter t. So that would just give me z equals to 6. Okay. Now, this is the thing now. I need to find the values for the parameter t that will actually parameterize this line so that it is just a line segment that would go from P to Q only. How do we determine that? Well, we need to substitute values of t to find out what are the values that will give me the points from here, which is from P all the way to Q. So I usually try this, t equals 0. So what happens if I substitute t with the 0? Then we're going to get x equals to 0, y is equal to 6 minus 0, which is going to be 6, and z equals to 6. We're going to get the point 0, 6, 6. Guess what? That is my starting point P. And then I start increasing the value of t until I get my two desired points for the line segment. So t equals to 1. So if I substitute the t with the 1, the first one is still 0. Then right here will be 6 minus 12, which is negative 6. And the last one would be, if I substitute a 1 on the t, there is no t, so it will just be z equals to 6. And what do you notice? That we got the second point, 0, negative 6, 6. That means that the parameters, the values of the parameter t that will make this line go from point P to point Q only, it would be any value of t from 0 all the way to 1. And these are my parametric equations, and those are the values of the parameter that will give me the line segment just from P to Q. So since this line segment goes from P to Q, then we're going to sketch it. So P is 0, then the value of y is 1, 2, 3, 4, 5, and 6, and the value of z is 6. 1, 2, 3, 4, 5, and 6. This is where the P is, and it moves in the direction of Q. Q is 0, which is my x, so there is no x. Then it's going to go to the negative y, which is negative 6. So it would be negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. And then the z is positive 6, so it's 1, 2, 3, 4, 5, and 6. So this is going to be my point Q. And this vector moves in the direction from point P, all the way to point Q. So it's going to go from here all the way to here. So we need to give it direction, so it's going to move in this direction. Next. Now, this is a formula that we're going to use right now to basically determine the distance. If I have a line and I want to find the distance from a point that is not on the line, of course, to that line, so the distance will be given by the by basically the line segment perpendicular to that line. So because when you want to go from when you want to find the shortest distance from a point to a line, you need to go perpendicular to the line. So this is the distance we want to find, and basically the formula to find the distance from a point to a line, what we need to do is we need to get we need to find some point on that line. Okay. So we need to find some point on that line, so we call that point P, and then we need to find a vector that goes from that point P to that point S. Okay, and then we're gonna do we're gonna find the magnitude of the cross product of some vector V that is parallel to that line. Okay, with the line that we created, so we can make basically a right triangle. Okay. So we find the magnitude of that vector PS that we got from some point on the line to that to the point that we're trying to find the distance of, with the cross product with the vector V that is parallel to the line, and then we're gonna divide it by the magnitude of that vector V. So this will give us the shortest distance from that point to whatever line. So let's go ahead and use find and solve this problem next. Find the distance from the point to the line. So I'm going to call this my point S. Okay, so we can use the same format as the formula. So this is the line right here. I need to find two things. I need to find one point that is on this line and a vector that is parallel to this line. Okay. To find a point that is on this line, all I have to do, substitute some value of x into the t, some value of x, some value of t into the equations for x, y, and z to find just some specific point on that line. And it can be whichever point. Okay, and I'm going to call that point P. So what if we substitute t equals to 0? That would be the easiest we can do. If I substitute the t with the 0, that's going to give us x equals -2, y equals -4, and z equals to 6. So we're going to call that point P. That's -2, -4, and 6. And now, how do I find a vector that is parallel to this line? Very simple. Remember that these parameters that we have here, we can say that is like the slope of the line. So if I want a vector that is parallel to it, then a line that is parallel to another line, they must have the same slope. So I want a vector V that has the exact same slope as that one, which in this case is going to be using the same components. We're going to call it 2i because that is my x component, plus 1j, which is this component right here, and then minus 3k, which is the k component right here for the z. And this vector will be parallel to this line. Now, we already have vector v, and we already have the points P and S, but we need the vector that goes from P to point S. Okay, that's another thing we need to find. Let's go ahead and find that. To find that out, we're going to subtract the components. It would be S minus P, since it goes in the direction of S. So, would be 1 minus -2. It would be 3. So that would be 3i. Then the y components, it would be 4 minus -4. That would be plus 8j. And -4 minus 6, that would be minus 10 and k. Okay. So we already found all the necessary information for us to find the distance from the point S to this line. Okay, we already have the vector PS, we already have the vector V, and everything is there. So to find the distance, let's use the formula for the distance. What we need to do is it's going to be the magnitude of the vector PS with the cross product of vector V divided by the magnitude of vector V. So first thing we're going to do is find the cross product of PS with vector V. okay, before we can actually use the formula. So I'm going to copy down the formula and I'm going to put it on the side, since we still need two more things to find. Okay, so that's the formula that we need. And I'm going to erase it from here so we can find the missing information. Okay, so let's find the cross product of PS with vector V. So let's use the determinant form. So with the components I, J, and K, so knowing that PS equals to 3, 8, negative 10, and vector V is 2, 1, and negative 3. So we're going to have I times the determinant of, cover the row and the column, and you have the values 8, negative 10, 1, and negative 3, minus J, remember it's plus minus plus when you do it, so minus J times the determinant of, you cover the row and the column of J, and that leaves you with 3, negative 10, 2, negative 3. Negative 3. And the last would be a plus K times the determinant of, the values that we get covering the row and the column of K will leave us with 3, 8, 2, and 1. And let's finish it. So that's going to give us I times 8 times negative 3 is negative 24, minus negative 10 times 1 is negative 10, and then minus J times 3 times negative 3 is negative 9, minus negative 10 times 2 is negative 20, and then plus K times 3 times 1 is 3, minus 8 times 2 is 16. Okay, and so we're going to get that the cross product of vector PS with V is going to be negative 24 plus 10, it would be negative 14. So it would be negative 14I, then negative 9 plus 20, that would be 11. 11 times negative J would be minus 11J, and 3 minus 16 is negative 13 times K, which is negative 13K, minus 13K. So last thing that we need to do on this guy, we need to find the magnitude of that cross product. So that would be the square root of negative 14 squared plus negative 11 squared plus negative 13 squared. That would give us 196 plus 121 plus 169. So let me open up a calculator really quick. So let me do that right now. Give me 1 sec. Oh, not that. Okay, I think it's 400 and, let me see, plus 121 plus 169. That would be 486. Okay. And then we need to simplify it. Okay, we need to simplify that. So it is a factor of 81. So 81 is a factor of 86. So we can break it down into this. So the magnitude of vector PS and V, it would be the square root of 81 times the square root of 6, which is equal to 9 square root of 6. Okay. Then we need the magnitude of vector V. That's another thing we need. So vector V, remember, was 2I plus J minus 3K. So to get the magnitude, it would be 2 squared plus 1 squared plus negative 3 squared. So the parenthesis was supposed to be for this one. Okay, So the magnitude of vector v would be the square root of 4 plus 1 plus 9. That would be square root of 14. Okay, so we're ready to find the distance from that point, from the point S that we had at the beginning to the line that with the parametric equations that we were given. We're gonna get the magnitude of the cross product of PS and V divided by the magnitude of the vector V. So the magnitude of the cross product is 9 square root of 6 divided by the square root of 14. One thing is that since we were going to divide them, I think I didn't actually have to reduce this, simplify it. Okay, but it's fine. So it is always best. So let's go ahead and use this division, and let's estimate the answer to the nearest. Let's use one decimal place. So it would be 9 times the square root of 6, and that divided by square root of 14. And so the distance from the point that we were given to the line with the parametric equations given is about 5.9 units. So if we sketch it, that will be the approximate distance from the point 1, 4, negative 4 to this parameter, to these lines. Okay, it would be 5.9 units. Next. Now, these are the equations for a plane. Okay. Now, just know one thing that we discussed on one of the previous problems is that if I want to find the equation of a plane given a normal vector, if we have a normal vector, that is, normal vector means a vector that is perpendicular to the plane. Remember what we talked about is that vector will always, any vector that has the same components as the components of a plane will always be normal or perpendicular to the plane. So if I know a normal vector, and I can use those components as the components for any given plane. So these are the 3 components for the plane, and to find the equation, this is called the component equation, in which is 3x plus by plus cz equals to some constant. But to find that constant, we're going to be utilizing our initial point. This x0, y0, and z0 will be any point that lies on the plane. Any point that lies on the plane, we can use it as our initial point. Okay, and that will help us to obtain the equation of a plane that is perpendicular to some vector, normal to some vector. So this one tells us that we want to find the equation for the plane through the point 355 and normal to the vector 8i plus 4j plus 4k. Okay, so this is our equation. Since this vector is normal to the plane, that means that these are going to be the same as the components, the A, B, C components of that plane. Okay, and that vector passes through my initial x0, y0, and z0, which is 3, 5, 5. So those will be the values for the initial, for one of the points of the plane. That's all I need to get the equation in terms of x, y, and z. So let's substitute everything we know. So that would be 8 times x minus x of 0, which is 3, plus b, which is going to be 4, times y minus y of 0, which is 5, plus c, which is 4, times z minus z of 0, which is also 5, equals to 0. Then we're going to distribute this to simplify, so it would be 8x minus 24. 24, that's what I said, not 28, plus 4y minus 20 plus 4z minus 20 equals to 0. I'm going to put the f8x plus 4y plus 4z together and all the constants together. So negative 24 minus 20 is negative 44, minus 20 is negative 64, equals to 0. And to put it in standard form, let's move the constant over to the other side. That will give us the plane 8x plus 4y plus 4z equals to 64. So this plane right here is going to contain the point 355, and also it will be perpendicular to this vector. Next, find the equation for the plane through these 3 points. Remember that one thing we discussed before is that if I just get 2 vectors, PQ and PR, from PQ and from P to R, and I get the cross product of those 2 vectors, that will give me a vector that will be perpendicular to those 2 vectors. So that is the first thing we're going to need to get the equation of the plane, because the equation of a plane that passes through some of these points, one of these 3 points, okay, and it's going to have the same ABC components as a vector that will be perpendicular to these vectors. Okay, so first thing that we need to do is find the vector PQ. So for PQ, we're going to subtract the components Q minus P. It would be 5 minus negative 3, minus negative 3i, plus, then it's negative 1 minus 3, and then j, and then plus, and then 4 minus 3, and that's going to be my k. We're going to do the same thing, but now from P to R. So we're going to do R minus P, which is 1 minus negative 3i, plus negative 1 minus 3j, plus negative 1 minus 3k. So my vector PQ is going to give us 8i minus 4j plus k. And my vector PR, it's going to give us 4i minus 4, that's a 1? Yeah, right? Yes. So minus 4j minus 4k. Now, if we get the cross product PQ with PR, that is going to give us a vector that will be perpendicular to those 2 vectors. And basically that's what we want, because the components of that new vector will be the ABC components of the plane. Okay. So PQ is 8 minus 4 and 1, and PR is 4 minus 4 and minus 4. So for the I component, we're going to have I times the determinant of negative 4, 1, negative 4, negative 4, minus j times the determinant of 8, 1, 4, and negative 4, and then plus k times the determinant of 8, negative 4, 4, and negative 4. That will give us the following. So my vector PQ cross vector PR, I'm going to call this a normal vector, right? So I'm going to call it vector n. Okay. So that's going to give us I times positive 16, negative 4 times negative 4 is positive 16, minus negative 4 times 1 is negative 4, plus or minus j times, and in this case is 8 times negative 4 is negative 32, minus 4 times 1 is going to be 4, and then plus k times a times negative 4 is negative 32 minus negative 4 times 4 is negative 16. So that normal vector is going to be 16 plus 4, which is 20i. Then negative 32 minus 4 is minus 36j. Well, that would be minus 36 times negative j would be plus 36j. And negative 32 plus 16, it would be minus 16k. Okay. Now, we want a vector that is, a plane that is perpendicular to this vector, because this is a normal vector, remember? A plane that is perpendicular to this vector, and it passes through one of these 3 points. So let's go ahead and use the piece of 0 as the point. Okay, it can be any of them. Okay, so I'm gonna use the negative 3, 3, 3 as the x of 0, y of 0, and z of 0. Okay, so the plane would be in the form a times x minus x of 0 plus b times y minus y of 0 plus c times z minus z of 0 equals to 0. So the a component, these are my ABC components of that vector. That's the a component, that's the b component, and that's the c component of the vector. C component. And that you already have my x of 0, y of 0, and z of 0 up there. We just need to replace those values to get the equation of the plane that is perpendicular to this vector. Okay, and that passes through the point x of 0, y of 0, and z of 0. I could have used any of the other points, but I'm just taking that first point P as the basis. Okay, so it would be 20 times x minus negative 3 plus 36 times y minus 3 plus, minus 16 actually, that will be the next one, minus 16 times z minus 3 equals to 0. So we're going to get 20 times x plus 3 plus 36 times y minus 3 minus 16 times z minus 3 equals to 0. Then let's multiply it. So that's 20x plus 60 plus 36y. Then that will give us minus 108 minus 16z, then it will be plus 48 equals to 0. Then we're going to combine the constants, and I'm going to put the x, the y, and the z on the side. Combine the constants, so it would be 60 minus 108, that would be negative 48 plus 48, that would be 0. So this is the equation for the plane. And what we can do is that we can reduce it. You see that all of them can be reduced. So I can divide everything by 4. So I can make this plane a little simpler. So and if I divide everything by 4, that's going to give us finally the plane 5x plus 9y minus 4z equals to 0. So this plane will basically pass through these points, all of them, and it would be perpendicular, of course, to this normal vector that we obtained, which is 20i plus 36j minus 16k. And the main thing is that it passes through the given points that it tells us right at the top. So if you do this as an example, like if I substitute the given points into the equation, you should see that they should be equal to 0, so they should satisfy the equation of the plane. So if I substitute the negative 3, 3, and 3, which is point P, back into the equation, that's negative 15 plus 27 is 12, minus 12, it's going to give you 0. If you do the same thing with the points Q and the point R, you should get the same thing, that is going to give you also a 0. For example, point R, 1, negative 1, negative 1, that will be 5 minus 9 is negative 4, plus 4, it's going to give you a 0. Okay, so Next question. Now we're going to find the equation for the plane that passes through the point 6, 1, and negative 1, and it's perpendicular to the following line. Perpendicular to this line. Okay. Alrighty. Let's go ahead and begin with this one. For this question, let's keep one thing in mind. That remember that from these parametric equations we can get a vector from the components of the parameter t. So that vector, so I'm just gonna call it vector v for now. Okay, so it's gonna be 1i plus 2j minus 3k. What do we know about that vector with relation to this line? It's parallel to the line. However, but I want an equation of a plane that is perpendicular to this line. So, and what do we know about a line that is perpendicular? Vector, a vector with these components I, j, and k. Those components will be the same as since this line. If we say that it is perpendicular to the plane, then those components will be the same as the components of the plane. Okay, so this is parallel to this line, but we can say, we can say that it could be a plane that is, so that we can use the same line. That line will be perpendicular to the plane. So if it is perpendicular to the plane, then it would have the same components as ABC for that plane. And we wanted to pass through the point p of 0, which is 6, 1, and negative 1. Those are my x of 0, y of 0, and z of 0. So let's get the equation for the plane. So this is going to be 1 times x minus 6 plus 2 times y minus 1 minus 3 times z minus negative 1 equals to 0. So this is going to turn to a positive 1. So it's going to give us x minus 6 plus 2y minus 2 minus 3z, then minus 3 equals to 0. Then we're going to put the x's and the y's and the z together right here. And the constants, negative 6 minus 2 is minus 8. Minus 8 minus 3 is going to be minus 11 equals to 0. We move the 11 over to the other side. That gives us the following plane. X plus 2y minus 3z equals to 11. So this plane is going to be perpendicular to this vector, but this vector is parallel to this line, so that means that the points on this line are on this vector, right? And it contains the point 6, 1, negative 1. How can we check if it contains this point? Just substitute the values and you will see that it satisfies the equation. 6 plus 2 is going to be 8. 8 minus negative 3, which is 8 plus 3, that's equal to 11. So it contains that point. Okay. And like I said, this, because of this vector v has the same components as the components of the plane, then this vector is perpendicular to the plane. But at the same time, this vector passes, that the points on this line pass through this vector, right? Okay. All right. Now the next thing that we need to talk about is this. We want to find the points of the point of intersection of the lines below, and then we're going to find the plane determined by these lines. Okay. Now, find the point of intersection. First of all, to be able to find the point of intersection of this line, we need to set a system of equations. That's basically what we need to do. So, to get the system of equations, what do we need to do? We need to say, okay, if we want to find the point of intersection, then we want to find the point for which these two x values are the same, these two y values are the same, and those two z values are the same for these parametric equations. So we want to find where 3t plus 2 equals to the s plus 3. We want to find where the 5t plus 3 equals to the 3s plus 6. And we want to find where, at what values of t and s would 2t plus 2 be equal to negative 5s minus 3. So for this, the first thing we need to do is, choose a method that you want to use. And I'm going to use the method of addition. And I'm going to use the first two equations. Okay? But first, let me fix them. So I'm going to move this constant over to the other side. And I'm going to move the s over to the left side, right here. So that would give us the following equation. 3t minus s equals 1. Let's do the same thing here. Let's move this constant over to the other side, and let's move the 3s over to this side. That will give us the equation 5t minus 3s, and this cancels right here, equals 2, 3. So, using these two equations, I'm going to solve it using the method of addition. 3t minus s equals 1, and the other equation, 5t minus 3s equals to 3. Now, it doesn't matter if we don't use the third one. We can use any of the two equations to find the solution. Okay, so I'm going to use these two. So if I want to use the method of addition, I'm going to eliminate the s's. So I need to multiply this one by negative 3 to make it a positive 3, and it cancels with negative 3 right here. Right? So it would be a negative 9t plus 3s equals to negative 3. And then I'm going to bring down this equation here, which is 5t minus 3s equals to 3. And I'm going to add them. So if I add them, we're going to end up with negative 4t. This cancels out, equals to 0. So t is equal to 0. So if I want to find the value of s, I can just replace the t equals to 0 into any of the equations, either the first equation, the second, or the third one right here, whichever. So I'm going to use, let's say, this one right here. Okay. So we already know 5t, and t is equal to 0, so I'm going to replace the t with the 0 here. 5t minus 3s equals to 3, so that would be negative 3s equals to 3, so s equals to negative 1. Okay, so to find the point of intersection, this is what we need to do. The point of intersection of the two lines. All we need to do is we need to substitute either the t equals to 0 or the s equals to negative 1, either on these three equations, substitute the t equals to 0, or the s equals to negative 1 on these three equations. They should generate the same point. Okay? So, I think it's easier to substitute the t equals to 0, so I'm going to go ahead and do that on the top ones, because those are the ones with the t. X equals, so if I replace the t with the 0, that would be 3 times 0 plus 2, that would be x equals to 2. If I replace the t with the 0 on the y, so it would be 5 times 0 plus 3, that would be y equals to 3. And if I replace the t equals to 0 onto the z equals to 2 times 0 plus 2, that would be z equals to positive 2. So that gives us the point of intersection of the two parametric equations of the two lines, which is 2, 3, 2. This is the first thing that we needed to find on this problem, the point of intersection of the two lines. Now, second, what do we need to do next? Okay, we need to find the equation of a plane that passes through this, that will contain those two lines, right? So, I can use the components of these lines, remember, as my I, J, and K, 3, 5, and 2. Okay, but those components will be parallel to that line, right? So we're gonna say that those components will be parallel to the line. So I'm gonna say I'm gonna call that vector U, for example, and that would be 3I plus 5J plus 2K. I can also create a vector V with the components of the second line, which is the value in front of the S is 1, so that would be 1I, then plus 3S, that would be plus 3J for the Y, and then minus 5S, that's for the Z, so it would be minus 5K. Okay, but these two lines, we cannot use these as the components for the plane, because these lines are parallel. They're parallel to the plane that we're looking for. So we want them to be perpendicular. We need a vector that is perpendicular to the plane, because remember that the components of a vector that are perpendicular to the plane will be the same as the ABC components for that plane. Okay? How do we find a vector that is perpendicular to these two vectors that belong to those two lines? The answer is in front of us, which is the cross product. So all we have to do is get the cross product of U and V, and that will give us a normal vector, a vector that is perpendicular to that plane, and thus it would have the same components ABC as that plane. So let's get the cross product. That would be I, J, and K, and the components are 3, 5, and 2, and these ones are 1, 3, and negative 5. So let's do the determinant. So it's I times the determinant of 5, 2, 3, and negative 5, minus J times the determinant of 3, 2, 1, and negative 5, and then plus K times the determinant of 3, 5, 1, and 3. I'm going to call that vector N, which is normal, N for normal, okay, perpendicular. So that will give us I times the vector, I times the component, negative 5 times 5 is negative 25, minus 3 times 2, which is 6, minus J, and then times 3 times negative 5 is going to be negative 15, minus 2 times 1 is going to be 2, and then plus K, and that would be 3 times 3 is going to be 9, minus 1 times 5 is going to be 5. And that gives us the normal vector. Let's put it here. Negative 25 minus 6 is negative 31I. Then negative 15 minus 2 is negative 17 times negative J is plus 17J. And 9 minus 5 is going to be plus 4K. So this plane, it's going to be, since it is a normal vector, it will be perpendicular to this line is going to be perpendicular to the plane that we're looking for, and thus these are going to be the same as the ABC components of that plane, and we know that that plane passes through some point. Since this is the point of intersection of the two lines, that means that that plane passes through that point. So 2, 3, and 2. We can use that point of intersection as one of the points for the plane. X of 0, Y of 0, and Z of 0. So now we can go ahead and find the equation of the plane. A times X minus X of 0 plus B times Y minus Y of 0 plus C times Z minus Z of 0 equals to 0. So A is equal to negative 31, so it will be negative 31 times X minus 2 plus B, which is going to be 17 times Y minus 3 plus C, which is 4 times Z minus 2 equals to 0. Let's go ahead and finish it. Negative 31X plus 62 plus 17Y minus 51 plus 4Z minus 8 equals to 0. Then let's combine the values. So that will give us negative 31x plus 17y plus 4z, and then combine the constants. 62 minus 51 is 11. 11 minus 8, that's going to give us a 3. So it will be plus 3 equals to 0. So I'm just going to move that 3 over to the other side. So the equation of the plane will be negative 31x plus 17y plus 4z equals to negative 3. And this plane, it's going to pass through the point of intersection of the two lines, okay, which is 2, 3, 2, and it will be parallel to these two lines because it is perpendicular to the cross product of the two vectors that are parallel to those two lines. And you can check that it contains the point of intersection, very simple, by just substituting the coordinates. And even I'm going to assure you that if you substitute any parameter t equals to 1, t equals to 2, t equals to 3, and you generate whatever point on this line, or if you substitute the s with any number, s equals to 1, or s equals to 2, or s equals to 3, the point that you generate from these two lines, when you replace it into this equation, into the equation of this plane, it should satisfy this plane. So in other words, they should be on this plane. Okay, the next thing that we need to do is find the point P at which the line intersects the plane. Find the point P at which the line intersects the plane. So we want to find out where do this line intersect that plane. Okay, when we want to find the intersection, basically this x value for the line, this y value for the line, and that z value for the line must be on that plane, meaning that if I substitute them, they should satisfy the equation of the plane. So what I'm going to do, I'm going to substitute the value of x into that plane, the value of y into that plane, and the value of z into that plane to find the values of t that will satisfy this equation. Because in this equation, it intersects with the plane, that means that this line must be on that plane. So if I substitute the values of x, y, and z, that's going to help me to solve for the value of t for the intersection of that line and this plane. So let's do that. So we're going to go with this equation, which is 8 times x, and x is going to be 6 plus 3t, plus 9 times y, but the y is going to be 5 plus 8t, and then minus 3 times z, but z is going to be negative 3 plus 5t, and that is equal to the 18. So that gives us a 48 plus 24t plus 45 plus 72t plus 9. Then it's going to be, plus 9 minus 15t should be equal to 18. Then let's combine like terms. So the 48, the 45, and the 9, and also the 24t plus the 72t minus the 15t. So 72 plus 24, 96t. 96t minus 15t, it would be 81t. So it will give us 81t, and then 48 plus 45, it would be 93. 93 minus, 93 plus 9, I'm sorry. 93 plus 9, it would be 102. So it would be 81t plus 102 equals to 18. So for 18, so minus 102. So that will give us 81t equals to 18 minus 102. Again, right here at the end, we're going to end up with the fraction, but it doesn't matter. So it could be a fraction. So that will give us a negative 84. And then divided by 81. So let's see if we can reduce it. I'm just going to do it here. Divided by 81. And as a fraction, I don't think you can reduce that. Yeah, you can reduce it by 3 actually. And that gives you negative 28 over 27. Okay, so that's the value of t that will create the intersection of this line with this plane. Just remember that a plane and a line you know, that right here they're going to intersect at some point, and that's what we're trying to find. Okay, so we have some plane, and then we have a line. We want to find that point of intersection of the plane and the line. Okay, so how do we find that point of intersection? Last, we already know that the point of intersection occurs when t equals to negative 28/27. So we're going to substitute that back into the x, y, and z of the parametric equations. Okay. So we know that x is going to be equal to 6 plus 3 times t, but t is negative 28/27. And then the y, it's going to be 5 plus 8 times t, but t is negative 28/27. And z, it's going to be the same as negative 3 plus 5t, but the t is going to be negative 28/27. And that should give us the x, the y, and the z coordinates for the point where the line, this parametric equation, intersects that plane. So let's find those values, and let's just give it as a fraction, as a reduced fraction. So it would be 6 plus 3 times negative 28/27, and I'm gonna leave it as a fraction. That's 26/9. Second is 5 plus 8 times negative 28/27, and I'm gonna leave it as a fraction also. That's negative 89/27, and the z would be negative 3 plus 5 times negative 28/27, and that should give us, as a fraction, negative 221/27. And so the point of intersection is going to be 26/9, comma, negative 28/27, comma, negative 221/27. That is the point of intersection of the line and the plane. Okay, so next. Now we want to find a parametrization of the line in which the planes, these two planes, intersect. Find the parametrization of the lines at which these two lines intersect. Okay, the way to approach this is the following. First of all, since we have a plane, x plus y plus z equals to 3, that means that that plane will be normal or perpendicular to the following vector. I'm going to call it vector u. I plus j plus k. Remember, because we have the same components 1, 1, and 1 on this vector, on this plane, that on this vector. So remember that the components of the plane in a vector will generate a vector that is perpendicular to the plane. Likewise, if I create, let's say, a vector v from this plane, call it, that would be a component of 1 as the value of a, so that would be 1i, plus, and then for the value of y is a 1, so that would be 1j, and there is no k, so it would be plus 0k. So those 8 components will give you a vector that is perpendicular to that plane. So we want to find the parametrization of the line where these two planes intersect. Okay, so in other words, one thing that you need to keep in mind is that since these two vectors are perpendicular to the planes, okay, then those are perpendicular. If we do the cross product of them, they will give you a vector that is parallel to the planes. Parallel to the planes will be the same thing as having, as the same as being parallel to the line that we're trying to find. Okay, and if it's parallel to the line, then we can use those components for that vector as the components for the parameter t for the x, y, and z for that line. You know what I'm saying? So first of all, let's find the vector that is parallel to the planes, because these are perpendicular. So we want the parallel to the planes to find the parameterization of the line that will be parallel to that vector. Okay, so to get that, we're going to use the I, J, and K, and we're going to do the determinant form, which is 1, 1, and 1 for U, and 1, 1, and 0 for V. So that U cross V is going to give us the following. So I times 1 times, well, I'm just going to write it all, so I'm not going to skip any steps here. So that would be with the times the determinant 1, 1, 1, 0, minus J times the determinant 1, 1, 1, 0, and then, hold on, plus K times the determinant 1, 1, 1, 1. Okay, so let's do the cross product. U cross V, it's going to be I times 1 times 0 is 0, minus 1 times 1 is 1, minus J, and then 1 times 0 is 0, minus 1 times 1 is 1, plus K times 1 times 1 is 1, minus 1 times 1 is 1. So that cross product is going to give us negative 1i, or negative I. This is going to be negative 1 times negative j, which is positive 1j, or positive j. And then 1 minus 1 is 0, so that would be plus 0k. Okay? So this, I can use these as the components of the line that will be on the plane. So that will be parallel to the plane, basically. Okay? Now the only thing we need is, now we need at least to find one of the points that will be on that plane. Okay? So to find one of the points on that plane, so we need to find the intersection of those two planes, basically. Okay? So to find the intersection of those two planes, I'm gonna do something a lot easier to find the intersection, because this one has 3 variables and this one has 2. Both of them have the x and the y and the x and the y. So what I'm going to do, what if we let the y be equal to 0? So that would be the simplest, so we can eliminate the y from both of them. Okay, let's use a point for which the y, or even where the x is 0, because both of them have x and both of them have y. So, but I'm just going to pick the y. So what if the y is 0? Then we're going to get x plus z equals to 3 for the first one. And if the y is 0, we're going to get x equals to 4 for the second one. But since we already know that x is equal to 4 from the second, we're going to substitute it right here to find the value of the z using the first equation. So 4 plus z equals to 3, so z equals to negative 1. Okay, so we found one point. So one of the points that will be on both planes will be the point x, which is 4, comma y, which is 0, comma z, which is negative 1. That will be one of the 2 points on those planes. We can say is one of the intersections of those planes. Those 2 planes intersect at, this is one of the points of that intersection. Okay, there might be more points, because when 2 planes intersect at a line. So that line of the point of intersection could have many, many, many points of intersection. So for example, let's say this is one plane, and let's say, I'm just going to say this is the other plane. When those 2 planes intersect, they will intersect at some line, right? But again, we're not interested on the whole line of intersection. All I need from that intersection is one point, and we already got it. Okay? So now we need to get the parameterization for a line that will be on those 2 planes, basically, and that will contain this point, which is part of the intersection of the 2 planes. and we know that this line is, since it is parallel, the two vectors u and v were perpendicular to the planes, so that means that the cross product of them creates a vector that is parallel to the planes. Mainly, we can use the components of these vectors, of this cross product with this point to get the parametrization for the line that will be on those planes and that will pass through this point, which is part of the intersection of the two planes. So, for the x component, what we're going to do is we're going to do x, which is 4, minus 1. This is a 1 right here, minus 1t or minus t. For the y component, it would be the y value, which is going to be the 0, plus the j component, which is plus 1t. And for the z value, it would be the z component, which is negative 1, and then plus the k component, which is plus 0t. And that will give us the parametric equations: x is equal to 4 minus t, y is equal to 0 plus t, which is t, and z equals to negative 1 plus 0t, which is just negative 1. This is one of the millions of parametrizations that we can get for the line in which these two planes are going to intersect. Okay, we can get many other parametrizations, but this is an example of such parametrizations. Next, now for the next part, we're going to use the formula of how we can find now the distance from a point, but now to a plane. Okay, the distance from a point to a plane. The formula says that we need to get the magnitude of the dot product of a vector that goes from that point, from some point P on the plane to any point S that we want to find the length of. S is the point that will not be on the plane, so we want to find the distance from that point S to that plane, basically. Okay, and on that plane we're gonna have some point P. Okay, so that's basically what we need to find. So we need to find that vector PS, and then we need to do the dot product of that vector with a normal vector of that plane in the direction to that plane. Because remember that the normal vector of some vector, a normal vector to a plane will be perpendicular to a plane, but that normal vector will be the smallest possible normal vector in the direction of that vector n. Remember, because it is n divided by the magnitude of n means the unit vector in the direction of n. So this is what the formula tells us. We're going to get a unit vector in the direction of n, and we're going to do the dot product with a vector PS, which is from a point P on the plane to the point S that we want to find the distance of. And once we get the magnitude of that, that should give us the distance from that point S, the shortest distance from that point S down to any given plane. This is what that is going to give us. Okay. So, first question here is find the distance d between the point S equals 394 and the plane 5x plus y plus z equals to 15. Okay, so one thing that we can do here is that first of all, we need to find a vector that is normal to the plane. To find a vector that is normal or perpendicular to any given plane, we can use the same components as the component of the plane. So it will be 5i plus 1j plus 1k. That would be a vector that is perpendicular to that plane, since it has the same components as the components of the plane. But then we need a point P on the plane, because we need to find a vector PS that goes from the point on the plane to that point that is not on the plane S that we want to find the distance of. So how do we find a point P on this plane? Very simple. We can just find the easiest point that we can pick from this plane would be the intercepts. either the x-intercept, the y-intercept, or the z-intercept. How do we locate those? By setting the x and the y equals to 0 will give us the z-intercept. If I set the y and the z equal to 0, that gives us the x-intercept. And if I set the x and the z equals to 0, that gives us the y-intercept. So what I'm going to do, I'm going to let the y and the z be 0 to find the x-intercept. So let's go ahead and use that point, the x-intercept. Remember, it can be any point. Okay? And for the x-intercept, I need to let the y be 0, and I need to let the z be 0. Okay? So 5x plus 1 times 0 plus 1 times 0 is equal to 15. So that gives us 5x equals to 15, which is going to be x equals to 3. So that gives us the point 3, 0, 0. That we're going to call it point P. That's the point on the plane. Okay? I need to find the vector PS. That is the next thing. Okay? So to find the vector PS, what are we going to do? Going from P in the direction of S, so we're going to do S minus P. So 3 minus 3 I plus 9 minus 0 J plus 4 minus 0 K. And that will give us the vector PS, which is 0I plus 9J plus 4K. Okay? And now what else do we need? We need a unit vector that goes in the direction of this normal vector. Okay? For the formula, we need that also. Okay? How do we find that unit vector? Well, first of all, we need to find the magnitude of that normal vector, which is going to be 5 squared plus 1 squared plus 1 squared, and that is going to give us a square root of 25 plus 1, which is the square root of 27. I don't need to reduce it because we're going to get a distance. So, like I said, we're not going to use this as one of the values, for the answer. So the answer is going to be just the distance from the point S right here to that plane. So now we're going to construct a unit vector. The n over the magnitude of n will give us the vector n in the direction of the unit vector, the direction vector. Okay, unit vector in the direction of n. So we're going to divide the components by their magnitude. So 5 divided by the square root of 27i plus 1 divided by the square root of 27j plus 1 divided by the square root of 27k. Okay, so now, what is the formula to find the distance from a point to a plane? It is the magnitude of the dot product of the vector PS with the direction of the normal vector. Okay, so what does it mean by the dot product? It would be that you multiply the I components, the j components, and the k components, and you add the results. So it will be the I components will be 0 times 5 over the square root of 27 plus 9, the j's, 9 times 1 over the square root of 27 plus, and then the k's, 4 times 1 over the square root of 27. And that would give us 9 times 1, which is 9 over the square root of 27 plus 4 times 1, which is 4 over the square root of 27, and that would give us the distance, which is going to be 4 plus 9, which is going to be 13 over the square root of 27. And the absolute value of that is just 13 over the square root of 27. And then we can just find the approximate distance by putting it in the calculator. So we can find the approximate distance from that point to that plane. So it will be 13 divided by the square root of 27 will give us a distance of 2.5 units. So if we were to sketch that plane and we were to sketch that point on the coordinate axis, the approximate length from the point to the plane would be about 2.5 units. Next, now we're going to find the distance from the plane 3x plus y plus 7z equals to 24 to the plane 3x plus y plus 7z equals to 9. Okay, so for this one, what we need to do is, first of all, look at the two planes. What do we notice? That both of those planes have the same x, y, and z components, meaning that this vector that I'm going to do, which is n, I'm going to call it n, because remember it's going to be normal because I'm going to use the same components as these components. Since both of them have the same x, y, and z components, a, b, c components, then we can create a vector that is normal to both of those planes. So it will be 3i plus 1j plus 7k. So this is a vector that is perpendicular to both of those planes. And then we need to find the magnitude of that vector because that's what we need it for the formula. For the magnitude would be 3 squared plus 1 squared plus 7 squared. That would be 9 plus 1 plus 49, which is going to be the square root of 59. So the unit vector in the direction of n, it's going to be n over the magnitude of n, which is 3 over the square root of 59i plus 1 over the square root of 59j plus 7 over the square root of 59k. Now, we need 1 point on this plane and 1 point on this plane so we can find the distance from one plane to the other plane. We need to find a vector from one plane to the other. So in order for us to do that, we're going to do what we just did on the previous problem. We're going to find one of the intercepts of this plane and we're going to find one of the intercepts of the other plane. The easiest intercept that we can find would be well, it doesn't matter, so it can be x or y or z, but in this case, for the way I see it, is that the easiest one would be the x-intercept, because 24 is divisible by 3 and 9 is divisible by 3. Some of the other intercepts will result in fractions, so I'm going to avoid fractions for now on this one. So let's find the x-intercepts for both. Okay, so to find the x-intercept of this one, we let the y be 0 right here, and we let the z be 0 right here, and that gives us 3x equals to 24, which is x equals to 8, and that gives you the point 8, 0, and 0. And let's call that point P. And then right here, let's do the same. Let the y be 0, let the z be 0, and find the x-intercept. 3x equals 9. So x equals to 3. So we're going to call that point S. And that would be 3, 0, 0. So now what we need to do, we need to find a vector from point P to point S. Any vector. And that would be from the intercepts. So it would be S minus P, 3 minus 8i, plus 0 minus 0j, plus 0 minus 0k. Right? And that gives us the vector PS, which is going to be negative 5i plus 0j plus 0k. And now we are ready to go. How do we find the distance from, basically we're going to use the formula for the distance from a point to a plane. So we're saying, for example, finding the distance from this point P, or this point S, to that plane, this one, or this point P to that plane 3x plus y plus 7z equals to 9. That's exactly what it's going to do using the formula. And the distance is the magnitude of the dot product of the vector PS with the unit normal vector in the direction of n. So we're going to multiply the components of these two. So we already have both of them. This is the normal vector in the direction of n. This is my vector PS. So multiply the components and add them. So that would be negative 5 times 3 over the square root of 59. Then it's going to be plus 0 times 1 over the square root of 59. And then plus 0 times 7 over the square root of 59. So that will give us the following distance, negative 15 over the square root of 59, but the magnitude of that, when you square it and you get the square root, it's going to give you the same thing but positive, right? So the distance is going to be 15, positive 15 over the square root of 59, and we're going to approximate it using the calculator. So the approximate distance between the two planes is going to be 1.95. About, I'm going to round to the nearest 10, so it would be about 2.0 units, right? So this will be approximately 2.0 units. So if we were to sketch the two planes, between them, basically this is what we're talking about. The two planes are parallel because they have the same components of x, y, and z, a, b, and c. So any point on this plane to any point on that plane, what it's telling you here is that they would have approximately 2 units in between the two planes. That's what that is telling us right there. Okay? And the two planes are parallel because we saw that they have the same components for x, y, and z, a, b, and c. Okay. Alrighty. Now we're going to go ahead and find the last question. We're going to find the angle between the two vectors, the two planes. To find the angle between the two planes, we're going to use the same formula for the angle between the two vectors. Okay, so all we're going to do is, we're going to get a vector that is normal to this plane. So that would be 3i plus 10j plus 0k, right? Then we're going to get another vector, I'm going to call this n1, and I'm going to call this n2. And that would be, or you know what, just to use the same formula that we already know, I'm going to call them u and v. Because we're going to use a common formula that we already know. This is going to be vector u, and this is going to be vector v, which is 9i plus 5j plus 10k. And these two vectors are normal to these planes. So what we can do to find the angle between the two planes, all we have to do is find the angle between these two vectors. That will be the same as the angle between the two planes. So to find the angle between the two vectors, the formula is cosine inverse of the dot product of the two vectors divided by the product of their magnitudes. Okay, so the dot product would be 3 times 9 plus 10 times 5 plus 0 times 10 divided by the product of their magnitudes. Let's go ahead and get the magnitudes of each one right here on the side. Magnitude of u would be 3 squared plus 10 squared plus 0 squared, which is going to be 9 plus 100, which is 109. Okay? And the magnitude of the vector v is going to be, let's calculate it, square root of 9 squared plus 5 squared plus 10 squared. That would be the square root of 81 plus 25 plus 100. That would be 206, right? Yeah. So 206, so square root of 206. So let's go ahead and use that to find the angle between the two vectors, and let's put it in the calculator. So it would be, make sure the calculator is on degrees. That's what we're going to find right now. Or you can find it in radians, it's up to you. Whatever the question asks, okay? So 3 times 9 would be 27 plus 50 plus 0, of course, which I shouldn't put it, divided by the product of their magnitudes, which is 109 times the square root of 206. And that gives us 59. So the angle between the two vectors is approximately to 59 degrees. This is the angle between the two vectors. Well, the two vectors, which in this case we're talking about the two planes. And this concludes section 11.5 about lines and planes in space.